So, Professor Loeb, your recent paper suggests that this object might actually be alien technology rather than just another comet. What exactly about the speed, the trajectory, the behavior leads you to consider this as a possibility?
Well, first, it's relatively bright for its distance, implying that if it's a solid object, it has to be 20 kilometers in diameter. That's twice as big as the giant asteroid that killed the dinosaurs 66 million years ago. And the previous objects we saw from interstellar space were only hundreds of meters in size. So there is just not enough rocky material in interstellar space to provide us with a 20-kilometer rock that appears once per decade.
Something gigantic just entered our solar system, and it's breaking every rule we thought we understood. 3I Atlas, a cosmic visitor from another star, has shifted its path in a way no natural force can explain. Scientists are stunned. If gravity isn't enough, what's really out there? Imagine a cosmic intruder hurtling through the solar system at over 130,000 miles per hour, more than 57 kilometers every single second. That is 3I Atlas, the third confirmed interstellar object ever detected by humanity, and instantly the largest of its kind ever seen. Its sheer presence is enough to unsettle astronomers around the world. But what is this giant, and how did we even find it? First detected on July 1, 2025, by the Atlas Survey Telescope in Chile, 3I Atlas immediately stood out, not just for its trajectory, but for its unprecedented size and brightness. Early predictions ranged wildly, and as data poured in, the object's true scale began to emerge. Some images suggested a nucleus up to 7 miles, or 11.2 kilometers wide, larger than Manhattan and about 10 to 20 times wider than its famous predecessor, Oumuamua. Other estimates, using high-resolution imaging from the Hubble Space Telescope, put a tighter range between 320 meters and 5.6 kilometers, but with a strong likelihood that Atlas is truly gigantic by cosmic standards. If these numbers hold, this is comfortably the largest interstellar wanderer humanity has ever glimpsed. But Atlas is not just big, it's active. Surrounding its icy nucleus, a ghostly cloud called a coma stretches for tens of thousands of kilometers. Measurements using the Grain Telescopio Canarias in July 2025 revealed this cloud to be up to 26,400 kilometers by 24,700 kilometers across, about twice the diameter of planet Earth itself. In near-infrared, NASA's SphereX mission detected a vast halo of carbon dioxide gas extending more than 340,000 kilometers from the nucleus, nearly the distance from Earth to the Moon. As Atlas moves closer to the Sun, these features intensify, casting a shrouded, mysterious glow across the darkness of space. Now, consider Atlas's path. Most objects within our solar system follow elliptical or oval orbits, paths defined by the familiar tug-of-war between gravity and their original momentum. Atlas, by contrast, plunges through space on a hyperbolic trajectory, its eccentricity at a staggering 6.08, almost a straight line. Only an interstellar traveler, born far beyond the influence of our sun and only briefly passing through, could arrive with so much velocity that not even the sun can capture it. That's why Atlas, unlike comets or asteroids we are used to, will never circle back. Its visit is a one-time event, a mystery speeding in from the distant stars and heading out again into interstellar darkness. Its movement isn't just straight, it's almost surgical. While previous objects like Oumuamua left scientists debating their cigar shapes, tumbling spins, and odd brightness, Atlas grabs attention with its sheer consistency and speed. Across every calculation, every orbital plot, one thing becomes clear. This object is traveling as if the universe itself made a loophole, allowing it to transit from galaxy to galaxy on some ancient journey. For reference, Oumuamua measured about 0.2 miles, 0.4 kilometers, while the next known interstellar object, Borisov, was roughly 0.6 mile, 1 kilometer. 3I Atlas is at the very upper end, much larger, faster, more dramatic in impact. So what is Atlas made of? Its surface, as pieced together by color imaging and spectroscopy, trends towards a dark red hue, likely a mix of cosmic dust, carbon-rich compounds, and the icy relics of its origin. There are signs of violent dust loss, suggesting that as Atlas bakes in sunlight, fresh material is released from deep below its blackened surface. Each eruption a memory from its long-lost home system far from Earth. But 3I Atlas is elusive. Its brightness at magnitude 14 or even dimmer makes it invisible to all but the most powerful telescopes. Even at its closest, skywatchers require professional-grade, large aperture instruments to glimpse its faint glow among the stars. In many ways, we are peering through a keyhole at a cosmic giant, struggling to measure it before it vanishes forever. And finally, there's its age and journey. Computer simulations tracking 3I Atlas's origin suggest it may predate Earth by several billion years, flung from its ancestral system after a massive chaos event. Some models place its birthplace in the thick disk of the Milky Way, a turbulent, ancient region where primordial comets and asteroids are shaped by gravitational violence. How long has it been racing through the void? What secrets are sealed in its ices, its clouds, its hyperbolic momentum? Is this the fate of all planetary systems, to throw their cosmic debris from star to star, ensuring that every solar system becomes a stage for alien mysteries? What we know is just the start. And as Atlas barrels closer to our sun, the questions are only multiplying. From the very moment 3I Atlas was detected on July 1, 2025, astronomers sensed something unusual, something that defies the very rules governing celestial motion. This cosmic visitor plunges through our solar system at blistering speeds, about 61 kilometers per second, or roughly 136,000 miles per hour. At that velocity, the sun's gravity cannot capture it. Its orbit is a hyperbola, meaning it's just passing through, never to return. However, what really sent shockwaves through the scientific community was the discovery that 3I Atlas's orbit changed in ways no known natural force can explain. Traditional physics tells us that objects like comets can alter their paths slightly due to outgassing, jets of sublimated gas acting like natural thrusters. But for an object of Atlas's vast size, these jets should not be enough to throw it off course, especially given that some observed orbital changes happen while it was too far from the sun to experience significant sublimation. Cutting-edge observatories, including NASA's James Webb Space Telescope and the Hubble Space Telescope, monitored 3I Atlas with extraordinary detail. What they found was baffling. While Atlas is indeed an active comet, spewing gas and dust as it nears the sun, the forces generated by these ejections cannot account for the precise changes in its trajectory. Scientists ruled out gravitational influences from planets or solar radiation pressure as causes for the orbital anomaly. Atlas's unexpected maneuvers even persisted when it was in cold outer regions of our solar neighborhood, far from the sun's warmth. Adding to the intrigue, 3I Atlas is set to pass near Mars in October 2025, where orbiting spacecraft will get a rare close look at this mysterious visitor. These unprecedented observations could offer new insights and hopefully answers to the puzzling forces at play. This phenomenon is unlike the two previously known interstellar objects, Oumuamua, which confounded scientists with its unusual shape and acceleration, and Borisov, a more typical cometary body from another star system. 3I Atlas is bigger, faster, and its strange behavior surpasses both with more extreme orbital shifts. The bottom line, 3I Atlas exhibits movement as if pushed by some invisible hand, forces at work that transcend our current understanding of celestial mechanics. This has led to theories ranging from conventional to speculative. Some researchers hypothesize internal fracturing or a porous, low-density core that might disrupt standard orbital predictions. Others entertain the bold possibility that Atlas might be an artificial construct, a kind of solar sail propelled by radiation pressure, representing technology from beyond Earth. While the scientific community remains cautious, these unexplained orbital quirks are undeniable, unleashing a wave of curiosity and debate about whether we are witnessing new physics or signs of extraterrestrial engineering. As Atlas approaches its closest point to the Sun, perihelion, on October 29, 2025, at about 1.36 astronomical units closer to Mars than Earth, astronomers worldwide prepare for a wealth of new data. This will be a critical phase to observe how the comet's velocity and path evolve, potentially unraveling the source of these mysterious forces. Ultimately, 3I Atlas challenges everything astronomers thought they knew about the cosmos. It may be that we are standing at the threshold of discovering unknown natural phenomena, or perhaps the first evidence that intelligent and advanced entities have sent probes across the stars. This question remains open, the tension mounting as we await more observations. What powers the invisible force that steers Atlas? Could it be nature's surprise, or something far more profound? The answer could redefine our place in the universe. When astronomers first observed 3I Atlas, they knew they were looking at something extraordinary, not just for its origin beyond our solar system, but for the strange way it behaved as it raced toward and through our cosmic neighborhood. 3I Atlas, as the third confirmed interstellar visitor detected, travels at roughly 61 kilometers per second, an incredible velocity that guarantees it is just passing by and not gravitationally bound to our Sun. Its highly elliptical, almost hyperbolic orbit makes it clear this is a visitor from another star system, arriving on a trajectory no comet native to our own solar system would take. Yet, what is far more puzzling is how this giant comet defies expectations in several ways. Once it was closely observed by powerful telescopes such as the James Webb Space Telescope, Gemini South Observatory, and others. Typically, comets alter their courses modestly due to a process called outgassing. As they heat up near the Sun, frozen ices sublime and produce jets of gas that act like tiny thrusters, pushing the comet and subtly changing its orbit. 3I Atlas does exhibit such activity, emitting gas and dust tails that grow as it approaches perihelion. Yet, for an object of this size, about 7 miles, 11 kilometers in diameter, these jets should not be strong enough or oriented sufficiently to explain the orbital deviations observed. Moreover, 3I Atlas's behavior is unusual because early on, at distances of 3 to 4.5 astronomical units from the Sun, too cold for intense sublimation, it already showed signs of unexpected brightness and activity, including an anti-tail pointing toward the Sun, a feature rarely seen in comets. Chemically, its composition further mystifies scientists. The comet's coma and tail show a high ratio of carbon dioxide to water, roughly 8:1, which is extremely rare for comets visiting from within our own solar system. In addition, spectral observations have detected nickel emission without the usually accompanying iron, an unprecedented finding in such objects. Thanks to the Vera C. Rubin Observatory and new high-resolution telescopes like Gemini South, astronomers can measure the evolution of these emissions and the dust coma in more detail than ever before. The comet's halo or coma extends tens of thousands of kilometers and continues to brighten and expand as it nears the sun. These features raise many questions. Has 3I Atlas undergone intense cosmic weathering in a distant star system? Is the comet an ancient relic from a planetary system unlike ours? Or does its unusual chemistry hint at artificial origins, perhaps pieces of advanced spacecraft or probes sent on an interstellar journey? Science leans on natural explanations first. The most accepted theory is that 3I Atlas formed in the thick disk of our galaxy, a region vastly different from our solar neighborhood, where materials and conditions produce bodies with chemical and physical properties unlike typical solar system comets. Its reddish color, akin to certain dark carbon-rich asteroids, suggests a surface coated in complex organic molecules and cosmic dust exposed to long periods of radiation and space weathering. Yet beneath this dark exterior lies icy material that jets out as the comet warms, producing the gaseous coma and tails seen by astronomers. What distinguishes 3I Atlas vis-a-vis other interstellar objects like Oumuamua and Borisov is its size and activity. While the former two were smaller and less active, Atlas's massive size and intense outgassing make it a unique laboratory to study interstellar chemistry and physics firsthand. These observations have not only confirmed Atlas as a comet, but have rewritten parts of cometary science, showing a wide diversity among interstellar visitors. In addition, the unusual behavior pushes astrophysicists to reconsider the limitations of our current cometary models, which were developed based on decades of observing solar system bodies. Could there be underlying physics or chemical processes unique to comets that originate in other planetary systems? To that end, 3I Atlas challenges planetary scientists and astrobiologists alike. Its trajectory, size, activity, and unusual chemical properties could offer clues to the conditions and materials that exist around other stars. As it passes perihelion around October 29, 2025, at about 1.36 astronomical units from the Sun, just inside Mars's orbit, the comet will reach its peak velocity and activity. This is a priceless opportunity. The intense solar heat will activate further sublimation, providing a broader chemical spectrum to analyze and potentially revealing more about its mysterious origins. This upcoming perihelion also marks one of the last chances for terrestrial and orbiting observatories to gather detailed data before the comet retreats back into interstellar space, disappearing from view until perhaps none of us will see anything like it again. The scientific world waits in suspense, knowing that every spectroscopic image, every particle count, and every brightness measurement could unlock new secrets about how planetary systems other than our own form and evolve. Could 3I Atlas be a messenger, not just a sneeze of cosmic dust, but a time capsule carrying the chemical story of ancient, distant worlds? And, what if anything, does this tell us about the possibility of life beyond Earth? As with all good mysteries, 3I Atlas ends this chapter not with answers, but with more questions. What will the next observation reveal? Is an even stranger visitor lurking beyond our telescope's sight? The journey to understand continues, and each discovery reshapes our view of the cosmos. As 3I Atlas speeds through our solar system, Its chemical fingerprint reveals a host of surprises that deepen the mystery of this interstellar visitor. From the moment it was detected, astronomers trained some of the most powerful telescopes in the world on Atlas, seeking to understand exactly what it's made of and how it behaves as it approaches the Sun. Data collected from facilities like the Gemini South Telescope, Very Large Telescope, and space observatories have offered unprecedented insights. One of the most striking discoveries is the unusual chemical composition within its coma, the cloud of gas and dust enveloping the nucleus. Unlike typical comets from our solar system, which generally show abundant water vapor when heated, 3I Atlas exhibits a significantly higher ratio of carbon dioxide to water, about 8:1. This is astounding because comets closer to Earth usually display much more water than carbon dioxide. Moreover, spectral observations have also detected the presence of nickel emissions, but curiously, no accompanying iron, something that defies normal cosmic chemistry. In natural cometary bodies and asteroids within the solar system, nickel and iron frequently occur together, making this separation highly unusual and puzzling. These chemical oddities suggest that 3I Atlas may have formed in a very different kind of environment than our typical solar system comets. The peculiar nickel without iron and excess carbon dioxide raise questions about its origin and the processes it has undergone during its journey through interstellar space. Polarimetric measurements, which study how polarized light reflects off the comet's dust, indicated that Atlas's coma has a unique composition compared with objects from our solar system. The pattern of light polarization closely resembles that observed in trans-Neptunian objects, icy bodies far beyond Neptune, indicating a mix of icy and dark, carbon-rich materials. Adding to the intrigue is the ongoing evolution of its coma as it nears perihelion. Observations show the coma increasing its size and brightness, reaching tens of thousands of kilometers in diameter, becoming more pronounced as the sun's heat intensifies sublimation. The tail of 3I Atlas is also growing more distinct. First imaged faintly by Hubble in July 2025, its dust tail extends tens of thousands of miles away from the nucleus in the direction opposite the Sun. By late August, larger ground-based telescopes like Gemini South captured sharper images showing the tail extending over 56,000 kilometers and evolving rapidly with changing solar radiation conditions. Its chemical behavior and emissions challenge conventional comet models. Scientists speculate that 3I Atlas's unusual composition might be the result of formation in an environment with very different elemental abundances than our solar system, a cosmic history involving intense cosmic radiation, collisions, or interactions with exotic interstellar materials, possible artificial origin or contamination. Though highly speculative, this hypothesis remains on the table due to the anomalous nickel without iron and other features. One of the most exciting aspects of this analysis is that 3I Atlas allows scientists to glimpse the chemistry and conditions in distant star systems without having to send spacecraft there. Every photon collected, every spectrum studied is a message from millions of light years away, carrying stories about the building blocks found there. This understanding could illuminate how planetary systems form and evolve in the galaxy's thick disk, where Atlas likely originated, a region markedly different from our solar neighborhood. The data gleaned may also contrast with the more familiar chemistry of comets, like 2I Borisov, showing the enormous diversity of materials drifting across the universe. As Atlas reaches its closest point to the Sun on October 29, 2025, at about 1.36 astronomical units, roughly between Earth and Mars, the the comet's sublimation and chemical changes will accelerate, offering a unique window to capture even more detailed measurements. At perihelion, the increased solar warmth will likely drive new jets of gas, modify dust emission rates, and possibly reveal trace elements or compounds hidden until now. This moment is critical. It combines maximum visibility with peak activity, a rare alignment allowing astronomers to probe the comet's secrets more closely before it speeds back toward the vastness of interstellar space. Ultimately, the chemical analysis of 3I Atlas is more than a scientific curiosity. It is a cosmic detective story, offering hints about how materials travel across the galaxy, potentially delivering the ingredients for life or even signs of other civilizations. The deeper we look, the more this visitor challenges what we know about cosmic chemistry and what might be waiting in the unexplored depths of space. In October 2017, the discovery of one Oumuamua, the first confirmed interstellar visitor, shook the astronomical community and captured the public's imagination worldwide. Now, 8 years later, 3I Atlas has entered the scene as a new cosmic mystery, reigniting debates and raising new questions about what crosses into our solar system from the vast galaxy beyond. At first glance, Oumuamua and 3I Atlas seem to share some traits. Both are interstellar objects traveling on hyperbolic orbits at high speeds, meaning neither is gravitationally bound to the sun, and both are here for a single fleeting visit. However, the differences quickly become striking upon closer inspection. Oumuamua was relatively small, approximately 400 meters long, while 3I Atlas is immense, with estimates suggesting a diameter up to 7 miles, 11 kilometers, making Atlas easily 20 times larger and possibly covering an area similar to a small city or island. Both objects exhibited unexpected behavior. Oumuamua's acceleration and tumbling motion baffled astronomers. It showed small but measurable deviations from its predicted orbit without visible signs of outgassing, leading to heated debates about whether it was natural or artificial. Similarly, 3I Atlas displays enigmatic orbital shifts, but unlike Oumuamua, it shows significant cometary activity, with jets of gas and dust detected as it approaches the sun. This activity should theoretically explain changes in trajectory, but in Atlas's case, the forces measured don't add up, suggesting something unknown is influencing its path. Scientifically, Oumuamua challenged accepted ideas of what interstellar visitors look like. Its elongated cigar-like shape, high reflectivity, and strange acceleration suggested it could be a fragment of a larger body, or possibly a probe equipped with a solar sail. This drew pioneers like Harvard's Avi Loeb to propose alien technology, a controversial yet fascinating hypothesis. With Atlas, the stakes are higher. Its sheer size amplifies the mystery, making natural outgassing less plausible as the sole cause of its unpredictable movements. Yet there are no clear signs of artificiality either. Another contrast comes from their chemical compositions. Oumuamua's surface was dark and reddish, coated in organic-rich material, somewhat similar to local asteroids. In contrast, 3I Atlas's coma has an unprecedented chemical signature with higher carbon dioxide levels and nickel emissions unusual by solar system standards. While Oumuamua appeared more like a rocky asteroid with unexplained acceleration, Atlas behaves more like a comet with active jets, but with chemical markers that challenge conventional cometary chemistry. These variations underscore the diversity of interstellar objects, showing that our galaxy sends different types of visitors, each bearing unique stories about their origin. The scientific community eagerly awaits further data during Atlas's close approach to the Sun in late October 2025. High-precision instruments will observe how its large cometary nucleus reacts to solar heating, potentially revealing volatile compounds and physical behavior that can help decode its origin. Comparing these two interstellar travelers raises profound questions. Is 3I Atlas just a massive comet from nowhere familiar, or could it represent a new class of objects entirely? Was Oumuamua an exception, a fragment from a destroyed planet, or just the first of many exotic bodies? What can these visitors tell us about planetary formation, star systems, and even life itself across the galaxy? Interestingly, recent analyses suggest 3I Atlas could be billions of years old, predating Earth by a significant margin, making it not only larger, but potentially much older than Oumuamua, whose exact age remains uncertain. This raises further questions about how such ancient and massive objects survive the violent conditions of interstellar space for eons. Their journeys challenge our understanding of cosmic debris exchange between star systems and highlight the need for continuous monitoring. As more interstellar objects get detected with next-generation telescopes, the diversity of their sizes, compositions, and behaviors will surely expand. And with it, our cosmic perspective. These objects are messengers from the far reaches of our galaxy, telling stories of creation, destruction, and the tumultuous dance of matter across light years. Whether natural or artificial, each new visitor like Oumuamua or 3I Atlas is a puzzle piece in the grand mosaic of the cosmos. The story of Oumuamua set the stage, but 3I Atlas takes the mystery to a new level. As observations continue, we may be on the cusp of rewriting star maps with knowledge gained from these extraordinary travelers, unlocking cosmic chapters only hinted at before, and pushing humanity's quest for understanding ever deeper. The peculiar behavior of 3I Atlas has baffled scientists and sparked a wide range of theories. Its unexpected orbital shifts, unusual chemical makeup, and immense size all challenge our current understanding of celestial mechanics and cosmic chemistry. To unravel this mystery, experts have proposed several hypotheses, some firmly rooted in known science, others venturing into bold speculation. 1. Internal fragmentation and outgassing. One of the most conservative explanations is that 3I Atlas is experiencing internal fragmentation. Like comets from our solar system, it could have a loosely bound, porous nucleus prone to cracks or breakage. Such fragmentation could release jets of gas and dust in unpredictable directions, causing the comet to behave erratically and adjust its path mid-flight. However, the size of Atlas, estimated at 7 miles wide, makes this explanation less straightforward. A comet of this scale would require enormous outgassing force to cause the measured deviations in its orbit. Observations so far show that the jets are not sufficient to produce such a magnitude of effect, especially since some trajectory changes occurred at distances too cold to sustain significant sublimation. Could the comet's internal structure be extraordinarily fragile, filled with hollow regions or low-density matter that bursts unexpectedly? If so, this could cause bursts of energy and material, propelling it in ways standard comet models do not account for. This hints at a more complex internal architecture than previously imagined. Recent observations also revealed that the comet is exhibiting a surprising color shift, from red to bright green, as it gets closer to the Sun. This change might indicate new materials being ejected or an increase in reflective icy particles in the coma, hinting at evolving activity that could contribute to unusual forces acting on the comet. 2. Low density or porous core. Hypothesis. Closely related is the theory that 3I Atlas's nucleus may have an unusually low density or be highly porous. Some have likened it to a fluffy comet, where large volumes within the object are filled with vacuum or gas pockets rather than rock or ice. Such a structure could make the comet more susceptible to non-gravitational forces. For example, radiation pressure from the sun or collisions with particles in space might have a larger effect on its path than on denser, more compact objects. If Atlas's nucleus is composed of fragile, loosely connected materials, the way it responds to solar heating and orbital forces could be radically different from comets we know well. This hypothesis challenges the standard assumptions about comet formation and survival in interstellar space. 3. Solar sail or artificial origin. Theory turning from natural to more controversial ground, some scientists entertain the possibility that 3I Atlas might be artificial, a probe or spacecraft propelled by a solar sail. This hypothesis gained traction when Oumuamua's acceleration defied conventional explanation, leading scholars like Avi Loeb to propose alien technology, a controversial yet fascinating idea. Atlas's orbital anomalies and unusual chemical signatures, nickel emissions without iron, for example, fuels speculation that it could be an engineered construct or fragment of one. According to this theory, its trajectory alterations might be controlled or programmed rather than random natural processes. The idea of a solar sail is not purely science fiction. Earth scientists have experimented with solar sail spacecraft, using sunlight pressure to propel thin reflective sheets through space. An advanced civilization might use such technology to explore the stars invisibly. Could 3I Atlas be a relic of such a mission? Or perhaps an autonomous probe operating in the far reaches of our galaxy? While speculative, this hypothesis is taken seriously by a few scientists due to the unexplained orbital behavior. 4. Unknown physics or cosmic forces. Another possibility is that our current physics models do not fully apply to phenomena in the outer reaches of the galaxy or in extreme interstellar conditions. 3I Atlas could be influenced by forces or effects not yet discovered or well understood. Examples might include gravitational influences from dark matter concentrations, subtle magnetic or electric forces, or interactions with the interstellar medium that affect the comet's motion or composition. If such unknown forces exist, 3I Atlas could be the first observed evidence, signaling the need to revise or expand classical celestial mechanics. 5. Exotic material composition. The unusual chemical signatures of 3I Atlas, high C, O2 to H2O ratio, nickel without iron, presence of cyanide compounds, suggest a material makeup vastly different from familiar solar system bodies. This raises the possibility that Atlas originated in an environment with a unique stellar nursery or planetary system chemistry, influencing its elemental and molecular composition. It also opens speculation about cosmic processing, how radiation, collisions, and interstellar dust cycles in the thick disk of the galaxy might create objects that defy conventional chemistry. Understanding Atlas's chemical nature will shed light not just on one comet, but on the galactic oceans of material from which stars and planets form. 6. Fragment of a larger celestial body. Some models propose that 3I Atlas might be a fragment torn from a larger exoplanet or asteroid during a catastrophic event, such as a collision or gravitational disruption. Such an origin could help explain its unusual size and peculiar path through space. If Atlas is debris from ancient stellar violence, studying it is like holding a piece of another solar system in our hands, offering clues about planet formation and destruction beyond Earth. Whichever hypothesis eventually gains ground, the study of 3I Atlas is set to transform our understanding of interstellar objects and the wider cosmos. Observatories worldwide, including the Vera C. Rubin Observatory and space telescopes, are preparing for detailed close-up observations during Atlas's approach around the end of October 2025. Scientists anticipate this will provide crucial data to support or challenge current theories, bringing us closer to solving this cosmic enigma. As 3I Atlas speeds toward its closest approach to the Sun, perihelion, around October 29, 2025, the world of astronomy braces for an unprecedented opportunity. This cosmic visitor, approximately 1.36 astronomical units from the Sun, about halfway between Earth and Mars, will reveal more of its secrets as solar heat intensifies its activity. The object's orbit, a hyperbola exhibiting the highest eccentricity recorded for an interstellar object, ensures its fleeting visit. It will swing close to Mars on October 3, 2025, within 0.21 astronomical units, about 31 million kilometers, allowing orbiters around the red planet, like NASA's Mars Reconnaissance Orbiter, to observe it with exceptional resolution. This close Martian pass is expected to produce some of the clearest images and spectroscopy ever captured of an interstellar comet. Mars orbiters might glimpse the evolving shape of the coma and tail in detail, complementing observations made by Earth-based telescopes and space observatories such as Hubble and James Webb. Following perihelion, 3I Atlas will pass near Venus on November 3, 2025, then will reach a minimum distance of about 1.83 astronomical units from Earth on December 19, 2025. Although the comet will not come dangerously close to us, this return in Earth's night sky presents a valuable chance to continue ground observations before it fades back toward the depths of interstellar space. The Vera C. Rubin Observatory, with its unparalleled survey capabilities, has already been tracking Atlas, and its ongoing data collection promises to reveal insights into the population of similar interstellar travelers, some yet undetected. In addition to routine telescopic work, the James Webb Space Telescope, JWST, has conducted infrared observations of Atlas using its NIRSPEC instrument. Planned further spectroscopy around perihelion will refine our knowledge of the volatile compounds sublimating from the comet's nucleus: water, carbon monoxide, carbon dioxide, and ammonia, each revealing the chemical essence of the comet's primordial material. JWST's ability to detect these compounds in the infrared spectrum will complement visible light measurements, painting a multifaceted portrait of Atlas's composition. This is crucial for understanding the makeup and formation history of objects from outside our solar system. As 3I Atlas moves away post-perihelion, the Hubble Space Telescope is poised to continue ultraviolet spectroscopy to map gas emissions and assess ratios of sulfur, oxygen, and other elements. These variations could shine light on the comet's evolutionary path and its exposure to solar radiation. This comprehensive observational campaign spans multiple wavelengths, distances, and angles, effectively turning 3I Atlas into a well-studied laboratory for interstellar chemistry and physics. An extraordinary chance, since returning interstellar objects are rare beyond imagination. Importantly, this expanded dataset will allow scientists to test models of cometary physics and astronomical dynamics beyond our familiar neighborhood. The stark differences with objects like Oumuamua and Borisov build an intriguing narrative about the diversity of visitors from other star systems. Looking beyond just 3I Atlas, the Vera C. Rubin Observatory, and upcoming space surveys are expected to detect dozens, perhaps hundreds, of such interstellar objects in the coming decades. These discoveries will enable astronomers to identify patterns, perhaps distinguishing comet-like from asteroid-like visitors, or unveiling clusters originating from the same galactic regions. Such results could lead to a new cosmic census, turning interstellar visitors from isolated curiosities into routine entries in our astronomical maps. This will transform how we conceptualize our solar system's interactions with the galaxy and expand the scope of planetary science. Last but not least, these objects also prompt philosophical reflection. 3I Atlas might be just one of many cosmic messengers bearing clues about the formation and evolution of stars, planets, and possibly even life. Its passage reminds us that our solar system is part of a much larger and dynamic celestial environment, and that mysteries still await discovery in the quiet reaches of space. The future of 3I Atlas exploration is bright, propelled by the combined efforts of observatories, telescopes, and the curiosity of mankind. What we learn from this interstellar visitor may rewrite textbooks, inspire missions, and fundamentally alter our cosmic perspective. As we close this chapter on 3I Atlas, remember this: what we have uncovered is just the beginning. This mysterious visitor could rewrite what we know about our place in the cosmos, or perhaps reveal secrets far stranger than we imagine. But the journey doesn't end here. What lies beyond our reach right now? What cosmic revelations await just beyond the stars? If you thought this was extraordinary, wait until you see what comes next.